the next topic that we are going to study today is related to gravitational potential. Gravitational potential is the potential energy stored per unit mass. So if we have 1 kilogram of a mass, how much potential energy is stored of an object, let's say a planet Earth, a moon, or a star, or in the field of any object, how much energy has been stored, potential energy has been stored in it, in 1 kilogram of that material. Potential energy per kg is called gravitational potential, and is minus gm divided by r, where g is the gravitational constant, m is the mass of the object, and r is the distance from the center of the object to that object whose mass we are, or to that point where we are calculating the gravitational potential. Okay, so the question is, find the gravitational potential V at the surface of the Earth. The Earth mass is 5.98 times 10 to the power 24 kilogram, and radius is 6.37 times 10 to the power of 6 meter. Okay, so solution. What we are given here is the mass of Earth. That's our m. And we are also given radius, and we already know g, which is 6.67 times 10 to the power minus 11 Newton meter square per kilogram squared. So V is equal to g m divided by r. G is 6.67 times 10 to the power minus 11. Mass of Earth is 5.98 times 10 to the power 24, and r is 6.37 times 10 to the power 6. And if we solve all these terms, 6.67 times 5.98 divided by 6.37, what do we get? Oh, also we have a negative sign here, because the significance of negative sign is, if we have a planet here, the closer you get to the planet, the energy increases, but in negative sense, that its potential energy is decreasing, like it's lower than zero. So if an object is at infinity, it has zero potential energy. You bring it closer into the gravitational field, its energy start decreasing, the object start emitting energy, so its energy become negative. That's why we have a negative sign with it. So what do we get? If you multiply, minus
6.2 times 10 to the power 7.
Minus 6.3 times 10 to the power 7, and is potential energy per unit mass, so is joule per kilogram. Okay. If you want to find this potential energy is equal to g m divided by r square. V is potential energy per unit mass, so it becomes g m divided by r square m. M will cancel out, and we get not r square, g m divided by r. So we get this. So what is the energy? If you need energy to move a mass, that's energy usually is the work done on a body, and work done is the transfer of energy from one form to another. So if you required energy to move a mass m through delta V, it means that you are doing work done on the object. And how do we define the work done? We define the work done, W, the work done on the object. This is the first portion. W, work done on the object, is F multiplied by the distance it has been moved, F multiplied by delta R. Okay, and is with negative sign, F dot delta R, because you when you pushing an object, when you move an object across a potential difference, so you are coming the potential difference, and there is a cosine of minus 180 as plus 180, which gives you a negative sign. So work done is equal to minus F dot F delta R, because the work, or you can simply say that the negative sign indicates that the work done on the object that has been moved in gravitational field, the work has been stored in that object. Okay, and when you release that object, that work will again be converted into kinetic energy. So the negative sign is the indication that this pen is here and I'm bringing it up, so the work I'm doing on it is against the gravitational field and it is being stored inside the pen, and when I will release it, this work in the form of potential energy will be converted into kinetic energy and the pen will fall down. So the negative sign is here, and this is our equation number 1, which is really simple. We derived it really simply from a basic principle that work is W is equal to minus F delta R. Thus the equation of gravitational field strength can also can we use the equation of gravitational field strength to reach the same result? Now let's define. Gravitational field strength is the negative gradient of gravitational potential. Okay, but we also know that gravitational field strength is force per unit mass. Let's call it A and call it B and compare these two because both are gravitational field strength. So minus delta V divided by delta R is equal to F divided by M. Okay, and what do we get from here? We get M into delta V divided by delta R is equal to F, or M minus M delta V is equal to F into delta R, and this M delta V minus M delta V is the work done on the object. So F delta R is equal to work done, or sorry, we can say from here minus M delta V is equal to work done. So we are using this equation to replace this by work done. So we use the value of G, we use the equation of G, and we reach the same result as we define the energy from our work equation. The work done or energy is equal to minus M delta V. So that's how we can use the definition of G, gravitational field strength, to derive the work done equation. Okay, and this is a really important equation then that we can use to find the work done on an object. So we define work done, delta W is equal to minus M delta V, and from here M will become equal to minus delta W divided by delta V. Okay, and we put the values we don't need the negative sign here. Delta W is equal to M delta V. Why don't we use the negative sign here? Because change in work is equal to M into change in potential. If it's a negative work done on the object, like if object has been moved up, the work done will have a negative sign, and also the potential will have a negative sign, and both the negative sign will be cancelled. If a positive work is being done on the object, so the change in work then in that case will be from positive to positive, will remain positive, but in this case the potential is higher here and lower here, so the change in potential will also be positive. So that's why both will remain positive. So if it's one negative, the other is negative. If one is positive, the other is also positive. M is equal to delta W divided by delta V, and we got the work 2120 divided by change in potential is 26.65, and what do we get? Is 80.0 kilograms. So the mass of pig will be 80.0 kilogram. Explained. And we are given some options A, B, C, and D. Okay. The options are capital G, gravitational potential, gravitational field strength, and M. So do you have an idea that which will have an effect? What we know, G is equal to minus G M by R square. Yeah, G is equal to G M by R square as no negative sign. So it from the formula it looks that do you have an option to pick which will affect it first? Because we have reduced the radius, let me change it for you. So R is equal to Gm divided by G square root. Now so look at this G. G is a universal constant. It doesn't depend on R or G or any other value. So it's independent of all these values. Gravitational potential, that is V, it doesn't depend on will it have any effect? Will the gravitational potential be changed if we reduce if a satellite is orbiting the Earth, what is the effect of the following value of following the satellite orbital radius? So will it affect the value of V, gravitational potential, if we reduce the radius of our orbit? So initially our satellite is orbiting this distance, let's say R, and now I have bring the satellite to R by 2 distance. So will the decreasing the distance affect the orbital radius? If we reduce the orbital radius, will it affect the gravitational potential?
Yeah.
How? Because gravitational potential V is equal to minus Gm divided by R. So yeah, there is an effect on V on the G2, the V on the R2, because the radius has been reduced. So whatever the potential was here the potential will be, gravitational potential will be doubled. Okay? Doubled up. Will it be double? Yeah, R by 2. So it will go 2 will go up and the gravitational potential will be double. So if you measure the gravitational potential here with respect to this position and then you measure with respect to this position, always remember that we measure the gravitational potential between 2 points. Okay? So if you measure the gravitational potential on this in the entire this orbit, like here, everywhere the gravitational potential will be same, and between 2 points the potential difference will be 0. But if you moving like this and this, the gravitational potential will change. Will it be affected by G? Yes, because if you put R is equal to R by 2 now, what will happen? You get R square by 4. So the value of G will be increased by 4 times. So yes, it will be impacted by V and it will be impacted by G. Does the mass changes? No, it's independent of mass because mass is also constant. Okay. So delta W is equal to M delta V. We got mass and we got V. Change in work is equal to 1.72 and the change in potential is 531 joule per kilogram. So if you multiply 531 by 1.72, what do we get? Solution. We know that the time period is equal to 4 pi square r cube divided by gm square root. So if we square both sides, time period square will become equal to 4 pi square r cube divided by gm, and square root will cancel out. Now we need to eliminate r cube. So gm is dividing on this side, it will go on this side and be multiplied. 4 pi square is multiplying on this side. When we take it to the other side of equality, it will be divided. Right? We are multiplying by gm by 4 pi square on both sides. 4 pi square. So gm will cancel out with gm 4 pi square, and we got r cube is equal to t square gm divided by 4 pi square. We need r, not r cube. So what do we do? We take the cube root on both sides. So taking cube root on both sides, r is equal to, here we use the sign of cube root, that is the power of cube root is 1 by 3 t square gm divided by 4 pi square. Now we just need to substitute the values. So what do we get? R is equal to cube root of t is 27.3 by day, each day has 24 hours, each hour has 60 minutes and each minute has 60 seconds. Multiply by g, which is 6.67 times 10 to the power minus 11 Newton meter square per kilogram squared. Mass of earth is 5.98 times 10 to the power 24 and divided by 4 into 3.14 squared. Okay, so if we multiply, divide and then take the cube root, what do we get? We get 5.62 into 10 to the power 25, cube root of 5.62 into 10 to the power 25 meter cube. So because it's a cube root, we take we can write it 56.2 into 10 to the power 25. So r is equal to 56.2 into 10 to the power 24 meter cube whole power 1 by 3. So this will become equal to 10 to the power 8, and the cube root of 56.2 is for the cube root of 64 is 4, so it's less than 4. It becomes 3.83 into 10 to the power 8 meter. Okay, is this clear? So we got this situation here where we have a star and we got two planets. Planet A is 8 into 10 to the power 8 meter away and its period is just 18 hours. The planet B is 1 into 10 to the power 12 meter away and its period we need to find. Okay, so what we got t square is proportional to r cube, which means t square by r cube is always equal to constant. You can also derive this from this, that t square is equal to gm r cube divided by 4 pi square. You can use this relation and you get t square divided by r cube is equal to gm divided by 4 pi square, which are constant. G is constant, m is constant, 4 pi. They are all independent of t and r. So the ratio of t to r is always constant and just depend on this. So we can write then the ratio of ta square divided by ra cube is equal to tb square divided by rb cube. So this ratio will remain because the ratio of the period to orbital radius ratio for this planet will remain same as this value, and also for the period of this planet to its orbital radius ratio will also be this value. So both the values are same. From here we can calculate the tb square is equal to ta squared divided by ra cube multiplied by rb cube. So tb squared is equal to TA squared multiplied by RB divided by RA cube. Okay, so TB squared is equal to, what's the period? 18. Because we are calculating in hours, so don't need to change into second. And RB, which is 1 into 10 to the power 12 divided by 8 into 10 to the power 8 and whole cube. So we also got TA squared, that's 18 squared, and it's TB squared. Okay, so if you solve this, TB squared will become equal to 6382 6328 12.5, and because this is TB square, what do we need? We need just TB, so we take the square root on both sides. 6328 2.5 square root, and TB is equal to, we got 795.495 hours, or if it's, you look at it, 795.49 is almost 800 hours. This planet takes like 800 hours to complete one round, and this planets take 18 hours. Okay, so the further you go away from this planet star, your time period also increases. This is something about the planets. So if this is the sun and this is the elliptical orbit, in elliptical orbits, like this is the sun here and the planet is moving here, so there is a time when the distance between the sun and the planet is shortest. So that's the closest point. When planet is very close to the sun, it's moving really fast, or any planet to any of its star in the universe. When it's close to its star or any satellite to its planet, it's close to its orbiting object, it moves fast, and when it's far away, it moves slow. So it covers equal area in equal time. That's the Kepler's second law of area, that if it's close, it will move fast and cover larger area. When it's slow, it will move slow and it will cover the same amount of area like this. So this is the law of area. So now when it is close to the sun, it's moving with the maximum speed. And when it's moving with the maximum speed, then we need to find its calculate the distance between the sun and Saturn. So the potential energy, the gravitational potential energy EP, is minus G mass of sun, mass of Saturn, divided by distance between the center of sun and Saturn. Okay, R, that's need to be found. We are given the elastic gravitational potential energy, so R become minus G mass of sun, mass of Saturn, divided by EP. So minus 6.67 times 10 to the power minus 11. Mass of sun is here in this case 1.99 into 10 to the power 30, and mass of Saturn is 5.68 into 10 to the power 26, divided by potential energy, which is minus 5.57 into 10 to the power 34. So minus and minus will cancel out, and we need to multiply 6.67 multiply by 1.99 multiply by 5.68 divided by 5.57. 1.3535 into 10 to the power 12 meter. So the distance between the Saturn and the sun is 1.35 into 10 to the power 12 meter. Now the next question, the next portion of this question is, after 1 year on the earth, not the Saturn year, because earth is somewhere here and Saturn is here. So it means that the orbiter, the year of the earth is smaller than the year of Saturn, because we just proved that in the previous, from t square is proportional to r cube, this relation. So he says that now 1 year has passed on the earth. What will be the speed of the Saturn? What? No, we don't need to find the speed, we just need to tell, will the speed of Saturn be higher or lower than its speed as in A part after 1 year, 1 earth year, we can say. So that's what they are asking us. Yeah. So because 1 year has passed, but the year has passed on the earth, so Saturn, if one Saturn year is passed, Saturn will again reach at this point. The closest a planet to a star, the highest its speed is. Any place other than this, the speed of planet will be lower than this point. So because the Saturn after 1 earth year is not closest to the sun, therefore its speed will be lower. Okay, so because it's not closest to the sun, it's not 1 Saturn year, it's 1 earth year. Yes, if it's 1 Saturn year, then it will be again at the same point that it will have the maximum speed. Okay, so that was it. And the next, you can also write escape velocity as v escape is equal to, because this value 2gm divided by r is also under root 2re multiplied by g. The re is the radius of earth and g is the gravitational field strength. So 2re multiplied by g is the same as 2gm divided by r. Okay, let's just use r for simplicity for all kind of material. So same, you can use any of these formulas. Calculate the escape velocity of earth. Question. Calculate the escape velocity of earth. Solution. Since v escape is equal to 2gm divided by r, so what do we get? 2 into 6.67 times 10 to the power minus 11, and mass of earth is 5.98 times 10 to the power 24 divided by r is 6.37 into 10 to the power 6 and whole square root. So v escape will become equal to, if you solve this, it will become equal to 1.1190 10 to the power 4 meter per second. Or you can just write it 11.2 into 10 to the power 3 meter per second. 10 to the power 3 is kilo, so 11.2 kilometer per second. So if any object is given the speed of 11.2 kilometer per second on the surface of Earth, it will escape the gravitational field. So if we need to send up any object out into the outer space, out of the gravitational field, how much energy initial speed it requires? 11.2 kilometer per second. No matter you give the 11.2 kilometer per second speed to this pen or a truck or a big house or a rocket or a ship, if it is given 11.2 kilometer per second initial speed, it will escape. So it's independent of the mass of the object. It doesn't mean that heavier object require higher speed and smaller object require smaller speed. Yes, the energy required by higher object is more and the energy required by smaller object is less, but the speed for all kind of objects is same to leave the gravitational field of Earth or for other planets. You can use this formula actually to get the same result. If you use 2 into 6.37 10 to the power 6 multiply by 9.81 and take the square root, you will again get 11.2 kilometer per second. Okay. So the question here is that we have a satellite which is going in this orbit, and then the orbit radius has been reduced to 1 by 2. Like if it was r, now here is our center. So from here this was r and this has become r by 2. Here its time period was t, and now find the new time period. Okay. So what we say that t by r cube is equal to t square by r cube is equal to constant. So let the new time period be t new and new distance be, new radius be r new. Then t square by r cube is equal to t new square divided by r new cube. Here's always they are also given us the new r, that is r new is equal to original r divided by 2, because the distance has been halved. Okay. So what do we get? T square divided by r cube is equal to t new squared divided by r divided by 2 cube. Okay. So we put the value of r new, t square divided by r cube is equal to t new square divided by r cube divided by 8. And since we got t new square divided by r cube divided by 8, so what do we get? T new square multiplied by 8 divided by r cube. Okay. So this will become equal to t square divided by r cube is equal to 8t new square divided by r cube. R cube will cancel out and we get t new, which is 1 divided by 8 t. T new square is equal to 1 divided by 8 t squared. Okay. And now we can just take the square root on both sides. So t new is equal to t square divided by square root of 8. And square root of 8 is 4 multiplied by 2 square root, and square root of 2 is 2, so 2 square root 2. So t new is equal to, sorry, not t square, t divided by 2 square root 2. So the new time period will be reduced by the factor of 1 by 2 square root 2. By this factor, the new time period will be reduced. So we got time period for near satellite and the radius of near satellite and the radius of far satellite. Okay, and we need to find the time period for away satellite. Again the same rule, time period for near satellite squared divided by r of near satellite squared is equal to time period for far satellite squared divided by r of far satellite cube. Okay, and we need the time period for far satellite square is equal to time period for near square multiplied by r far cube divided by r near cube. Okay, and now we got t near is 42 hours multiplied by r far, which is 3.95 times 10 to the power 5. No, sorry, r far is 4.84 times 10 to the power 5 and divided by near one is 3.95 times 10 to the power 5 and cube, and this is squared. So time period for the far satellite squared is equal to hours, or 966 could be 57 hours. But we need to take the square root. Okay, so we need to take the square root of this value as well in order to find the time period of far satellite. Okay, is this clear? Calculate Pluto's velocity when it's closest to the sun. So when Pluto is closest to the sun, we need to find its speed or velocity. And that's the beauty of physics, that we can actually find its velocity from this data when it's closest to the sun or any point if we know its kinetic energy. So solution, we know kinetic energy is equal to 1 by 2 m v squared. Okay, so v squared will become equal to 2 times E kinetic divided by m. Okay, because 2 will go on this side and be multiplied, m will go on the other side of equality and be divided. So v become equal to square root of 2 E kinetic divided by m, and speed of Pluto 2 times kinetic energy, which is this 2.4 times 10 to the power 29 divided by mass, which is 1.31 times 10 to the power 22 and whole square root. So the speed of Pluto, if you multiply 2 by 2.4, it becomes 4.8, and 4.8 divided by 1.31, 6.1 times 10 to the power, because this goes up, it remains like 10 to the power 7, and then you divide and move this 1 point here. So 6.1 into 10 to the power 3 meter per second. That's the speed of Pluto. So B, now that you know the speed of Pluto and you know the kinetic energy, at any other point you can find the potential energy, and from potential energy you can figure out its total energy and total energy, kinetic energy, and then you can do anything you want about the Pluto, like its speed, its orbital period, anything you can find. So the B part is when Pluto is at different distance from the Sun, It has gravitational potential energy. Gravitational potential energy EP is equal to minus 3.2 times 10 to the power 29 joule. Okay. What is its kinetic energy at this point? So here is Sun and somewhere here is Pluto moving in an elliptical orbit. Now when it was closest to the Sun, its energy was, total energy is E is equal to sum of kinetic energy plus potential energy. When it goes to any point, the total energy remains same. The kinetic energy at the closest point is maximum, the potential energy at the closest point is minimum. As it moves in the orbit, the kinetic energy reduces because the speed decreases, and the kinetic energy increases because the distance between the Sun and the Pluto increases. So that's why this one rule will remain same, that total energy is equal to Ek plus EP, and we can find the total energy from here, which is total energy is equal to kinetic energy for closest point 2.4 times 10 to the power 29 plus minus 3.9 times 10 to the power 29. So you can take 10 to the power 29 common and you get 2.4 minus 3.9. So the total energy of the Pluto will become equal to 2.4 minus 3.9 will become equal to minus 1.5 times 10 to the power 29 joule. So this is the total energy at the closest point, and the total energy will remain constant throughout the orbit. So now we can use this total energy for this point. So for any point, EP E is equal to Ek plus EP, and we got Ek is equal to E minus EP. So kinetic energy will become equal to total energy minus 1.5 times 10 to the power 29 minus, and potential energy is given here, minus 3.2 times 10 to the power 29 joule. So Ek will become minus 1.5 minus minus plus 3.2 and times 10 to the power 29 is common. So what do we get? Ek is equal to 32 1.7 times 10 to the power 29 joules. V scape is equal to square root 2g m divided by r. So V scape 2 into 6.67 times 10 to the power minus 11 multiplied by mass, which is 7.34 times 10 to the power 22, and radius, which is 1.74 times 10 to the power 6, and whole square root. So V scape will become equal to, if you multiply in these two, 2.37 times 10 to the power 3. Meter per second, or 2.37 kilometer per second. So this is the escape velocity of Moon. Earth has 11.2 kilometer per second and Moon has 2.37. You can use the other formula too. Vs is equal to square root of 2 radius of Moon multiplied by gravitational field strength on the Moon. It will become equal to 2 into radius of Moon is 1.74 times 10 to the power 6, and the gravitational field strength of the Moon is 1.6, 1.6. Okay, so v escape will again equal to 2.37 kilometer per second. Okay.